In the last video, we started into talking about Modbus and gave you an overview of Modbus and got up to this slide in the presentation where we outlined the operations codes or function codes that's involved in a Modbus request and a response. And so we said that of all the function codes, these are the ones that we concentrate on in this course, and we'll cover the majority of the functionality on a Modbus network. So on your Modbus handout, which is your primary resource or tool to be working with these presentations and labs and exercises, we have the 8 function codes bolded in red here, and those are the ones that we fully describe and use in our message interpretations and to create a Modbus message as well eventually at the end of this at the end of these lessons. Okay, so this is where we're picking up where we left off. So the first function code we're going to look at is function code 1, which is decimal 1 and also represented as a hexadecimal value 01. And what would that look like if we took it even further in terms of its binary value? That would be seen as a combination of ones and zeros in the 1 byte value of the function code. That would be 0000 corresponding to 0 for a hexadecimal value, and simply 0001. That would be the 1 byte value in the function code field, has 8 bits representing read coil status. So we're reading the value of a digital output. And a DO is a single bit point. Whose status is simply 0 or 1. It's either a binary 1 or a binary 0. So it reads the status of a logical coil or output or DO. So broadcast is not supported for a read command. So remember, broadcast is where in the address field you have a 0. So the address field is equal to 0, and that's where the master or the client sends out a 0 in the address field, sending an instruction to every device or every server on the multi-drop network. And it's certainly not expecting a response to that like it would in a read command, because it's sending the message to everybody at once. So if everybody at once tried to get on the network, you know there'd be a data collision. So broadcast is not supported for any read functions. And it says the maximum points is 2,000 per request. And we'll see why that is in a minute when we look at the response. Now, one thing it says here is Modbus is what's called byte orientated. And what that means, because it's byte orientated, is you cannot send a partial byte. You have to send a full byte. So what if that means that you only want to look at one single DI point? That's only 1 bit. 1 bit equals 1 point. So if we're only asking for 1 point, that means that we're only going to report a 0 or a 1 back in the data, but because the protocol is byte orientated, we would have to include that 1 as the point data, but we would have to fill up the whole byte with zeros up until the point data of 1, so that we could send a full byte. We can't just send a single bit. It would be out of place. It's byte orientated, as you can see essentially from using the Modbus handout sheet. All of those fields are organized by bytes. They're either 1 or 2 bytes or more in size, but they're never just a few bits. So the rest of this is what's called bit stuffed. This is called bit stuffed or bit padded. Okay, So if not a multiple of 8, remaining bits are bit stuffed with zeros or bit padded with zeros. And if we were to look at the request, and I just went and kind of wrote over that. Okay, so I just cleaned that up there so we can see the request and the response. So when it comes to the request, each and every one of these boxes that make up this formatting of the request is just like what you see in your Modbus handout. The first field we know is a 1 byte field, right? So 1 byte. We know the function code is a 1 byte field. Notice how here we have a box that's equal to the length of 2 with a little divider in the middle, which indicates that as far as a 2 byte, or as far as a start address, it's always a 2 byte value. A least significant byte over here and most significant byte here. So we have start address that's 2 bytes, number of points is 2 bytes. And then what is not easily seen, and what I think is worth mentioning, is that the CRC is actually also 2 bytes long. And so on your Modbus handout, you might want to even do a little bit of an edit. And every time you see the CRC, is just put a little divider there that might remind you and make sure you don't miss the fact that it's a 2 byte value. Okay, so remember we've got these different fields that make up these the formatting of the message. And when it comes to a request for a 0-1, notice how we have a 1 byte slave address, 1 byte function code, 2 byte start address, and a 2 byte number of points, and then it ends with a CRC. That's the request. But down in the response, we can have it's not going to be the same number of bytes for every response, because of course that will be dependent on the number of points. The size of the data field will vary based on how many points were asked. So we can confidently say that when it comes to the request, we only have 1, 2, 3, 4, 5, 6, 7, 8 bytes of data for the request. But when it comes to the response, it's going to be variable in size because of the number of points that are asked for. So let's suppose this. Let's suppose that we... Okay, so now let's look at the response for a 0-1. Remember, the maximum points that can be returned are 2,000. And that was indicated here when we looked at maximum points, 2,000. That's where each point is a single bit. So let's first of all figure out how many bytes it would take to report back 2,000 points. So if we take 2,000 single bit points and we divide it by 8, 2,000 divided by 8 equals 250. That means that the number of the number of bytes it would take to report back 2,000 points would be 250 bytes. So that means coil data here would equal 250 bytes. And this is really all related to the fact that, if you recall, we said this frame can only go up to 250 bytes, 255 bytes maximum. So if we had the maximum 2,000 points, it would take 250 bytes to report back those values. We know we have a 2 byte CRC here. We know we have a 1 byte address, a 1 byte function code, and in this case a 1 byte count. And what would the byte count be if we had 250 bytes? It would be exactly that, indicating there was 250 bytes of data to follow. And if we add that all up, what do we have? 250 plus 1, 251, 252, 253, 255, and that's where we get our maximum of 2,000 single bit points that can be reported back in a response. So so yeah, all of these maximum number of points is related to a Modbus message maximum being 255. Now notice how it says if it's not a multiple of 8, the remaining bits, because it's byte orientated, are bit stuffed or bit padded with zeros. Okay, so then we're looking at function code 02. What would that look like in terms of a binary value? All zeros corresponding to 0, 0, 0, 1, 0 corresponding to 2. The 1 byte value as ones and zeros would look like that. Notice how, again, it's another read function. Read input status, it's called. It's reading the state of digital inputs. That means broadcast is not supported. When you send out a request and you're expecting a response, you wouldn't use a broadcast. Everybody would be trying to talk on the network at the same time. So again, single bit points then. Maximum points that could be reported is 2,000 for the same reasons that we just looked at. And again, if not a multiple of 8, the remaining bits are padded with zeros. So what's really the difference between 01 and 02? One of them is reading or confirming a value in a register that was an output register, like a DO. That's a 01. A 02 is reading an input register, so it's a read-only function. So you won't find a function to write a digital input, but you will find it to read, and this is the one. When we look at the previous one, 01, we had a read function for a coil, but we're also going to find a write function for a coil because it's a output register or a control. So if you were to look on your Modbus handout, you see the formatting exactly like this. Notice how the request is formatted exactly the same way, with a 2-byte start address, a 2-byte number of points, and your slave address function code and CRC. You might want to put a little divider there again to indicate that that's a 2-byte value, or help you remember it's a 2-byte value. And then as far as the response goes, it's no different than the 01 in that there's a byte count. There's status data as opposed to coil data, because this is a DI value. And the maximum size this could be then is 2,000 points, which would take 250 bytes to report. Okay, and again, if it's not a multiple of 8, because Modbus is byte orientated, we would have to pad the zeros in that particular byte with zeros. It's called bit padding or bit stuffing. Okay, so let's take our first example here, and this is looking at a read input status. And when we're doing any Modbus message interpretation, the very first byte to look at in order to use your handout or to figure out the way the message is formatted is actually the function code, because it's the function code that determines the formatting of the message and where to find it in your Modbus handout. So if we were to be interpreting this message, the first byte we look at is this one right here, and then use that to locate the request format in our Modbus handout. So in the Modbus handout, remember we said that the first thing you should look at in terms of the Modbus message to zero in on the formatting of the request or the response is the function code. So that's going to be the second byte of the Modbus frame. Every time the function code will be the second byte. The first byte, of course, we know is the address. That's the unique slave identifier or server number. And those go from 1 to 247, with address 0 being a broadcast and address 248 through 255 being reserved addresses. But if you look at the function code would be one that you find here, and you can see all the different function codes. And then we would go down, once we've looked at the second byte to determine what it is, we would find its either request or response in this list. So notice how this is showing the formatting of the message. The formatting of, say, a 01 request indicates a 1 byte slave, 1 byte function, 2 byte start address, 2 byte number of points, and 2 byte CRC. That would allow us to take all the hexadecimal numbers that make up the message and essentially drop them in each one of these boxes, remembering that a 1 byte value is 2 hexadecimal numbers. So you just group it into groups of 2 and drop them one by one into these boxes, knowing that it's a 01 request. Allows you to drop it in. If it's a 01 response, it allows you to format it this way: the first byte, the second byte, the third byte, and then drop all the coil data in here, and you know that the last 2 bytes of any Modbus message, whether it be a request or a response, is a 2 byte CRC. So that's what you would do. And in the slides, we're looking at a 02. So we're looking at a 02, first identifying the function code for the request, and then dropping each one of those 2 hexadecimal numbers into each one of these boxes till we're done, and we're ending off with a 2 byte CRC. And I'll bring up the Modbus handout here when on the computer and split screen it in here or whatever, so that we can see how we're using it. So the first byte, of course, we know is 0A. So that's a value in hexadecimal. No, these are all values in hexadecimal to indicate the values of zeros and ones, really, that make up this Modbus message. So now if we look at interpreting it, notice how we started by interpreting the 1 byte value of 0A that was contained in the address field and converted it to decimal, because we're going to communicate our server addresses as numbers that are decimal as we know them. So we know 0A as equal to decimal number 10, so we would call this server number 10. So that's the address of the server or the remote that we're requesting this data from. Function code, of course, we'd look it up in our Modbus handout and see that it's a read input status, and we'd further write in here read DIs. We're looking to read DIs. What's the start address in the data map that we want to read? Well, remember, there's this data map with all these different data types in the data map. We're asking that within the data map we want to start at address 20. So what we did is we converted a 2 byte value. Notice how it's 2 bytes now. 4 hexadecimal numbers. 0014 when converted to decimal is 20 base 10. So we're looking at starting to read address start at 20 base 10. Number of points then, of course, is converted to decimal again, because that's how we translate numbers and quantities and things like that. So it's 40 base 10 points. We are reading 40 points. And then lastly, you have your CRC. Now notice how the CRC hasn't been converted, hasn't been changed to decimal or anything like that. And that's because a CRC is a code. So it's a code. So being a code, there's no reason to convert it to a quantity or a number. It's a code that simply comes from the algorithm that's run on all the ones and zeros leading up to it, and you get this specific CRC code, 3EF1. It has no meaning to change it to decimal. It's a code. So that's our 02 read input status. Okay, so now let's look at the response. So notice this is the response, and because it's a response, it'll be one that has a varying data field, and the data field will vary based on the number of points. So how many points did we ask for? We asked for 40 points, if you recall, and because each one of them is a single bit, that would require 40 bits. Now, 40 bits when divided by 8 bits in a byte would mean that would only require 5 bytes to return the single bit data. And notice how here the byte count is 5. 5 bytes will report back 40 points because in each byte there's 8 points because it's a single bit status. Okay, so notice how in the response we've echoed back the server address, we've echoed back the function code, and we know this is a normal response because we didn't have a 1 in the most significant bit for an exception. Normal response. So what follows is a normal response with a byte count and point data. This is all point data. And then of course you have your 2 byte CRC. So what does that look like? Device address echoed back as slave 10 or server 10. Function code echoed back as read input status with no flagging of an exception, so we're good. And then a byte count of 5. So we've got 1, 2, 3, 4, 5 bytes, because remember it takes 2 hexadecimal numbers to represent 8 bits. And if we look down at the point data that we see here, there's a couple of really important things we need to understand from this raw data. This is what's called raw data coming back. Is that how do we know what addresses belong to these points? Well, remember, we asked for a start address of 20. And really, knowing that that was the requested start address from the request is the only way we're going to know what the address association is from this response. But once we do have that information, such as the start address, what we can say for sure is that the least significant bit of the first byte, the least significant bit of the first byte, remember, this is the first byte, this is the second, third, fourth, and fifth byte down here. So this first bit is where we find the status for point 20. So let's say point 20 was corresponding to a switch where 0 was on and 1 was on. This would indicate that the switch was on because in address 20 we have a 1. All right, and then you just count up from there. So that means address 20 would be here. Counting up, this would be address 27. So the status of address 27 is a 0. Now you move around to the next order of addresses starting there and work your way up. And you keep on moving around, working your way up until you reach the last address. So each one of these bits has an associated address for it. So if we count backwards, this one is 35, 34, 33. Address 33 would be a 1. Okay, now notice how this one we asked for 40 points. So because 40 points is an even multiple of 8, there is no bit stuffing or bit padding, and each and every 0 and 1 here corresponds to a status for an address 20 through 59. So the last address is 59 to give you a total of 40 points. So the status of address 59 is 0 right here. Okay guys, hopefully that makes sense. We'll be doing more practice of course, but that's just to get us started. Okay, function 03 then is something called read holding register. And when we read a holding register, what we're doing is looking at an AO or an analog output, and it's also sometimes called a set point. So we're reading a set point. What was the set point value for pressure or temperature or motor RPM? We're reading a value in an output register. Now this is it says reads and writes the content. Well, it's a read-write register, but I should tell you that this is a mistake. We're not writing. It reads the contents of a read-write register. Broadcast, again, is not supported. No read command is, or no read function supports broadcast. Notice how we have 125 registers, and each register is 2 bytes. So here's heads up on another quiz question, and that is to ask, all Modbus multi-bit registers are what size? They're all 2 bytes. So multi-bit registers, like counters, multi-bit registers are all 2 bytes. And that includes AO, AI, and counters and accumulators. So any multi-bit register in Modbus is a 2 byte register. It's a 16-bit register. 2 bytes, 16 bits. So notice how remember we have a data field there, right? So again, we'll be able to relate the maximum size of the data field to the fact that we're limited to only 125 registers per request or for a response. So here's where we see the pretty much standard requests that we've seen. 1 byte slave address, 1 byte function code, 2 byte start address, 2 byte number of points, and then your 2 byte CRC. Now it's different though when it comes to the response, because if we look at the response, we have our slave address, our function code, our byte count, but now each register is 2 bytes. So that means even if we were only asked for a single point, 1 point, let's say the request was requesting 1 point of an analog output, that means that the byte count would be 2. Because each and every register, or each and every point, is 2 bytes. That means that even if we only ask for 1, the byte count will be 2. So you would never see byte counts of anything other than 2, 4, 6, 8, and so on. Whereas with a single bit register like a read coil status or a read input status, you can have odd numbers in your byte count. But for this one, it'll always be even numbers because each point is 2 bytes. Hopefully that makes sense. Now, that means that after byte count, like we've mentioned before, the maximum size this could be is 250 bytes, right? So if we have 250 bytes, and each point is 2 bytes, that means that you have 125 points as a maximum. Whoops, points. You have 125 points as a maximum. And that's what we said right up here, 125. Okay, read input registers. And this is another read. I think you're getting the idea. Broadcast is not supported. Maximum 125, 2 bytes per register because it's another multi-bit register. And this is analog inputs or AIs. So this is your voltage, currents, pressures, temperatures that are being read. And these are input registers. And so it's a read-only type register. Slave address function code. Start address 2 bytes, number of points 2 bytes, okay, 2 bytes CRC. Response, I think you're getting the idea, even though these are analog inputs and not outputs, they're an input register, not a holding register, but they're still 2 byte values. Each and every point is a 2 byte value. So if you wanted to read 4 points, that means the byte count would end up being 8 based on reading 4 points. Each point is 2 bytes, so the byte count would be 8 in order to report back each value. Okay, the first, just like the digitals or the single bit points, the first reported value is the first address. The second is the second address, and so on. So if you ask for 4 points, the first point would be the first 2-byte value, the second one would be the second, the third would be the third, and so on. And then you'd end off with your 2-byte CRC. Again, 125 registers maximum. Okay, let's take a look at this. If we look at this request, right, the first thing we would do to interpret this is to look at the function code and then look at 04 function code in our Modbus handout and see how it's formatted. And if we did, we would see a 1-byte slave address, 1-byte function code, 2-byte start address, so it would be considered as a whole value of 2 bytes, number of points, 2 bytes. So we consider it as a whole value, and then your 2-byte CRC. Okay, and we're going to figure out what this message is. Notice how now we're working with a different server, but it's converted to decimal because our server unique identifiers, our numbers, are always expressed as decimal. So 31 base 10 for 1F. Our code 04, which corresponds to read input register, is doing what? Reading analog inputs. So we're reading AIs here. What's our start address? Well, it's a 2-byte value we need to consider. So if we put that into our calculator, this is where you put your calculator into hex mode. And of course you can ignore the leading 0 for purposes of number conversion and say FA0, convert to decimal, and you'd get 4,000. So that means our start address for this analog input is 4,000. And then we indicate the number of points. And because we've got a 2-byte value that's equal to 3, it's only 3 registers that we're wanting to read. Okay, so that's the request, and it's a request to read 3 analog inputs, of which we know are 2-byte values, and we want to read a total of 3 of them, starting at address 4000. Here's our response now. So for our response, we have an echoed back device address, or an echoed back server address. We have an echoed back function code, so we know this is a normal response. Normal response, because there wasn't a 1 in the most significant bit of this function code from the response. That would be flagging an exception. So we don't have that, so we know this is a normal response, an echoed back function code. Notice we have a byte count of 6. And remember, we asked for 3 points, and each point is a 2-byte value. Because of that, our byte count will be 6, and this is address 4000 as a 2-byte value. This is address 4001, and this is address 4002 for a total of 3 points, each of which are 2 bytes, and then our 2-byte CRC. So if we go through what we just covered there, we're down to our actual register contents for address 4000. So as a hexadecimal value, this is our register contents. So how do we know that's hexadecimal? Well, the only way we know is from that. So from that, we know that hexadecimal value can be changed to a base 10 value. So that's what we did in each case, is change it to base 10. So that means the contents of address 4000 is 13,922, 4001 is 4,802, and the last one 39. Okay? Question is, how would you request AI data from point 209 and point 459 from a slave device? Well, let's look at these 2 addresses. If we were to ask for point 209, and in the same request we wanted to get 459, that is a greater range of points than a count of 125 will allow. Because remember, for an analog input, which is a 2-byte value, the maximum number of points in a request based on the size, the maximum size of that data field is 125 points, which we know equals 250 bytes. So could we ask for could we make a single request that would retrieve the points with such a span between them? No, we couldn't. So basically the only way we could do this, and this is really kind of pointing to a deficiency in Modbus, the only way we could do this was to send two separate requests. So you would send what would be your function code to read an AI? You would do a 04 request on point 209 for a count of 1, and then you do the same 04 on point 459 for a count of 1. But remember, that would take a request waiting for a response and another request waiting for a response, and that would be inefficient in its use of bandwidth or communications, I think, as you can tell. Doesn't happen very often, and because of today's high bandwidths and fast data rates, it's probably not an issue in most scenarios, but still, you get the idea by looking at what it's showing here. All right, now we're going to get into the write command. Write functions now. So here's where we look at our function 05. This name force is corresponding to writing a control point. And remember that our digital outputs, or our single bit points for control, Modbus calls coils. So in this case, we want to force or energize a single coil or a single digital output. So we can either force it on or off. And notice how here it's indicating two different, essentially, codes for writing that value. We have a byte-oriented protocol. We're using a 2-byte code, essentially, to tell the other end to write a 1 in that coil or turn it on. And then we would have the opposite as all zeros as a 2-byte value to turn it off. So essentially this is a code. What's the code to turn on? What's the code to turn off? So when we look at our handout indicates that we how the request is formatted. And of course, how would we determine that? By looking first of all at the function code, because the function code is where we're going to be able to look it up in our handout. So when we go to a 05 function code, we can see it's formatted this way right from our handout, with 1 byte value here, 1 byte value here, 2 byte coil number, 2 byte on-off indication, and that comes directly from here, right? It's a 2 byte value of FF00 if you want to turn it on, and it's a 2 byte value of all zeros if you want to turn it off. And then of course you have your 2 byte CRC. And a response then, it's interesting for this one, we have the exact same response coming back as an echo. So it's the exact same values all the way across here, exactly through. Now, that being the case, this is an example of just a couple of the Modbus messages where response and request are going to have the same 2 byte value for CRC. Because think about it, because it's echoing back, all these 1s and 0s are going to be the same. So based on the fact all the 1s and 0s are the same, the algorithm, the CRC algorithm, is going to give you the exact same calculated result. So this is an example where the CRC values will be identical from request to response. Now if we look at a preset single, this is for a set point or an analog output, setting the value of temperature, pressure, or speed on a motor. So it presets a value into a single 2-byte register. And remember, all Modbus multi-bit registers are 2 bytes by default, so that's 16 bits. 16-bit register. So if we were to look at the function code of 06, right, and look at finding that in our Modbus handout, you'd be looking at a hexadecimal value of 06, you'd be looking at a binary value of 0110 with a 4 there, 2 there. So that would give you a 06 binary combination, and this is the formatting. So what do you see? 1 byte, 1 byte, 2 bytes, 2 bytes, 2 bytes. And once again, for this 06, which is a write function for an analog output, notice how the response is an echoed back value with all the same values coming back. Okay. Now obviously if this was an exception, meaning it didn't like the request to write that analog output, if you remember in the function field, it wouldn't be echoed back. It would be echoed back with a 1 in the most significant bit, indicating an exception. So as long as there's no exception, and it's a normal response to the request to write, then it'll be the exact same values and it'll be the exact same CRC again, because it's the same binary value. So if we take a look at some of these messages, let's look at where we would start with, and this is some software we're going to use in the lab, and we'll use it next class. What we're going to, I'm going to give you a more introduction to this once we get to the lab, but let's just start with this first one that's shown in the line monitor of this communications analyzer. What do we see here? Well, we see a arrow pointing that direction. That's telling us this is a request. So once we know this is a request, then where's the first byte we're going to look at in order to interpret it? The second byte, right? Because it's the second byte that indicates the function code, and we know that each one of those 2-bit or 2 hexadecimal number groups is indicating a byte. So that's going to give us our 1-byte slave address, our 1-byte function code, our 2-byte start address, our 2-byte number of points, and then lastly our 2-byte CRC. So this is the way we would go about interpreting that as a raw message. We'd first of all look at the second byte and then look it up in our Modbus handout. And then from there we can interpret each one of those boxes. So I would interpret the boxes one at a time. Slave address, function code. I would consider this as a 2-byte value. I would consider this as a 2-byte value. And then there's no interpretation to do of the last 2 bytes. You would just call that the 2-byte CRC. So here's the example from that screenshot from the line monitor of our communications test set. And I just was going to use this as our example as how we go about it, because here we have a message that we've identified as a request, right? So we've identified it as a request, and we have the raw hexadecimal value. What is the first thing we do? The first thing we do is we look at the second byte, which we know is the function code. So then you would go directly to your Modbus handout and you'd look up 02. You would go to the 02 formatting for the request and essentially build the empty boxes that are going to allow you to interpret this message. So once you get to that Modbus handout, you can see you have a 1-byte box to begin, then another 1-byte box, then a 2-byte box, another 2-byte box, and then you end with your 2-byte box for your CRC at the end. Now we just go about interpreting each one of those boxes as per the handout. So if we look at the first one here, we know this is the address field. So the address field is the unique slave identifier. We know that we have addresses valid between 1 and 247, and you know that 0 is a broadcast, and 248 through 255 are reserved. Okay, so let's look at this one. This is a hex value of 0A, and 0x is a way of indicating you're looking at a hex number. If you were to convert that slave address to a decimal address, because when we're talking about identifying with a number, we're going to use decimal, we're going to say that the slave number is 10. So you're going to use decimal for that conversion. So slave number is 10. Now you're moving down with the next 1 byte value. 1 byte value of 02 in hex. We know it's essentially a code, and this function code is 02, which we know is read input status. And we know the function of that is to read digital inputs, digital input points. Okay, then we now interpret the 2 byte value. The 2 byte value is a 03E8. And now you're going to convert that to a decimal number. So you're going to have your calculator in hex mode. You're going to put in 3E8. And you're going to convert that to decimal. And you're going to get 1,000. So that means the 1,000 is the direct decimal conversion, and you're going to say starting DI address to read is address 1000. Okay, then you move on to the next 2 byte value, which you can see is 0010. Okay, when converted to hex 10, when converted to decimal, is equal to 16, right? So you can say whoopsie. You can say that's equal to 16, and then the meaning of that is number of DI points to read is 16 points. And then of course lastly you've got your F8C8. There's no conversion to do at all with CRC. You can just say that that equals CRC. And if you were to actually look on the internet and find a Modbus CRC calculator, you could actually put all of this hexadecimal information into that calculator and hit equals, and you would end up with a value of CRC like what you see there. So next thing we're going to do is look at exception codes now. So when we look at an exception code, there's really 4 things we say that can happen when the master sends a request. The first one is the remote receives the request without a communications error. All the 1s and 0s are in their proper spot. The CRC parses out properly, and there's no errors in any of the data, and it returns a normal response. And you know that our indication that it's a normal response will be that the function code is echoed back in the response without 1 being the most significant bit. You could have it does not receive the request at all, and then the master will start waiting for a certain amount of time for a response to come from that server. And if it doesn't get a server, or doesn't get a response, it goes into a communications timeout, or what's called a response timeout. So that would result in a response timeout. Then of course you have the remote receives the request with a communications error. No response will be sent, and timeout will be the same thing. We'll get another response timeout. Now the reason why this happened is because the server couldn't interpret parse the message properly to even understand that it was something being sent to it, but it was being sent incorrectly. There was a communications error. It received it, but it was indistinguishable. It couldn't even parse it, that is, put everything in the proper boxes in order to understand anything about it. So it just basically ignored it, and you have another response timeout. Now here's the one that involves an exception code. The remote receives the request without a communications error. It parsed it, but when it parsed it, it didn't understand or didn't like what the request was. And this results in an exception response. So the exception response has two fields that are different from a normal response. And that's the function field and the data field. Okay? Now, the thing is about an exception response, it will always be a total of 1 byte, 2 bytes, 3 bytes, 4 bytes, and 5 bytes. An exception response will always be 5 bytes in length. So it's the shortest response message. The data field is only 1 byte. And what's contained in the data field is the exception code. What's in the function field? An echoed back function code, but a 1 in the most significant bit, in the MSB, a 1 in the MSB. So the function code field returns the function code with an MSB being set to 1. So it returns the same function code, but it puts a flag in there, and it flags it by putting MSB to 1. The data field returns the exception code. So this is where students often make a mistake. They want to combine the exception code in the function field. That's not the case. It's the data field that contains the exception code. Okay, so here's a list of our exception codes. Let's look specifically at this response. Well, look at the length of this response. You can see it's 5 bytes. This is telling us that we have an exception response. And notice the direction of the arrow is indicating that this is a response. And notice how that in the request we had a 02. If you have a 02 and we look at the binary value for a 02, this is the binary value for a 02. This is what went out for the function code for that request. But what came back was a 1000010, which equals 82. So what went out was 02 function code. What came back was 82, indicating that there was a 1 in the most significant bit. It was indicating that it didn't like something, and the way that the server tells specifically what it doesn't like is it uses the address field. And this is the address field, and it's a 02. So that means our exception code that is found in the address field is 02, and we would look that up. And where will we find that? Well, we'll just, and where we see a 02. What it didn't like was their illegal data address. So what it most likely means is that the master was asking for a specific data type at the wrong address. And therefore the server said, I don't have digital inputs at that address, or I don't have analog inputs at that address. And this is the way it indicates so with an exception code. Okay, so that'll be the end of part 2. And the next thing we'll do is do practice exercises regarding this message interpretation.